Welcome back, everyone. We're almost to the final stretch of the course. Next week is our last week. And today is our last day doing real linear programming stuff. Next week we're going to do some graph theory algorithms for some problems that we've looked at from LP. And then we're going to look at integer programming. And then I need to come up with something interesting to talk about on the last day or two. So, I'll be doing that. Today is like I said, is our last day doing real LP stuff. We've covered how to solve LPs. We've covered how to find the dual of LPs. We've covered sensitivity of LPs. Today we're going to put a little bit of a spin on linear programming and talk about how we can deal with having multiple objectives that we care about. I'm going to do that. We're going to look at an example and talk about a few things, a few different methods, a few different results. So let's do it. So this lecture is called "Let's Start the Pareto Frontier," and we'll talk about what that is. But first, an example. So suppose we have, well, a little backstory. In my free time, I like to do woodworking. I've built a few tables, a few coffee tables, boxes, and decorative stuff. It's a good time. So I happen to know that these two woods, Bocate and rosewood, are very expensive woods. So maybe a high-end furniture factory would build dining tables and chairs out of these two woods. It could be. We're gonna suppose that that's happening, and we're gonna use this as our example. So suppose that this woodworking shop has an ongoing deal with a foreign sawmill that's going to supply them with 960 board feet of Bacote and 200 board feet of rosewood every month. A single table requires 80 board feet of Bacote and 20 board feet of rosewood. Each chair is 20 board feet of Bacote, 10 of rosewood. A board foot is just a unit of measurement that's common in the woodworking sphere. So we have this sort of feasible region. If x is the number of chairs, or correction, x is the number of tables, and y is the number of chairs. There's a typo here. This should be 12. Then we can model sort of the feasible solution space with this polyhedron. Two variables, two constraints, and non-negativity. So let's suppose that each table sells for $7,000. Well, I changed the model, but I didn't change the word problem. each table sells for $8,000, while a chair sells for $2,000. And the we're going to assume that the man-hour cost, the cost of production, is not relevant. We just want to maximize profit. Or perhaps this profits 7,000 or 8,000. So we have a relatively simple objective function here. Just maximize profit. So then we have an LP. The manager of our woodworking shop knows his way around LPs. So he's going to do the simplex method. And the first thing he does is simplify the LP he has just by dividing everything by a constant to get smaller coefficients. And then he does the simplex method. He says, we're maximizing, that's our smallest negative. B over A is 12 and 16 and change. So we pivot here. And this gives us the tableau 0, 0, 1, 0, 48, 1, and we already see here that this is optimal, so we don't really need to worry. We don't really need to compute the rest of the tableau. That's where he stops anyway. He says, hey, that's an optimal solution. There's no negatives in that. I can just find our solution and be done. So that solution is number of tables is 12. He wants to produce 12 tables every month. And no chairs. That's optimal, right? He solved it. He did it mathematically. He used simplex. Proven optimum. So he found the optimal solution. 12 tables and 0 chairs. But if we look carefully, I've drawn in the level sets of the objective function in the dashed lines there. We can see graphically that this has multiple optimal solutions. That whole facet is optimal. It has the same objective function value. So if we look back at the tableau, we can see that in our optimal reduced cost row here, there's actually a spare 0. The basis is only size 2. There's only 2 elements in the basis, but there are 3 zeros there, and that can indicate to us that we could pivot to a different basis without changing the objective function value, which in turn implies that there are multiple optimal solutions. If we look back at the at the LP itself, especially when we simplified it, we can see that these two statements, the objective function and that constraint, they're parallel to each other. So that implies that there could be multiple optimal solutions. Neither of these things necessarily mean that there are definitely multiple optimal solutions. You could have a degenerate point. You could have some redundant constraints. But it's signs that there could be multiple optimal solutions. So is this 12 tables, 0 chairs solution really the best solution? Probably not, right? He's making tables, but how do you sell tables if you don't have any chairs to go with them? So probably not. There are probably better solutions. So that manager gets fired for not producing any chairs. People want chairs. And a new manager is hired. This new manager knows that Dalbergia stevensoni, which is the tree that produces rosewood, is a threatened species. And she decides that she doesn't want to waste any more rosewood than is necessary. So she investigates their manufacturing process and finds that tables waste nearly 10 board feet of rosewood, while chairs waste only 2 board feet per chair. So she comes up with a new objective function that she wants to minimize. She wants to minimize waste. 10 per table, 2 per chair. So now we have multiple objective functions, and we need to come up with a few ways to deal with having multiple objective functions. Having noticed that there are multiple optimal profit solutions, maximal profit solutions, she formulates a new problem to break the tie. So if we come up here, back to our image, we notice that if we want to restrict ourselves to the space of optimal solutions, or profit optimal solutions, we're really only looking at what's been highlighted here in purple. We're looking at a line. In higher dimensions, it could be a facet of your however many dimension polyhedrons, polyhedra. Polyhedron. But in this case, it's really easy to sort of see what that is and express it mathematically. It may not be quite as easy for a higher dimensional problem, but solvers have ways of dealing with this, of doing this sort of ordered optimal solution method. So in this case, we can see exactly the feasible region we have. We just took our first constraint. This is the constraint that was parallel to the objective function. We made it an equality because all of our optimal solutions lie on that constraint. And then we bound it by the endpoints. So x can move between 10 and 12, y can move between 0 and 8. Since this is an LP, the optimal solution will be an extreme point of our polyhedron. In this case, our polyhedron is just a line segment excuse me. So there are only two extreme points in this case. So we can just compare the two with an argmin. So if we use 12 and 0, we're going to get 120 waste. If we use 10 and 8, we're going to get 100 plus 2 times 8 is 16, 116 board feet. So we have found a new solution, 10 and 8, that has the same profit as our original solution, but wastes slightly less rosewood. Excellent. That's what we want. So, from this perspective, 10 and 8 is actually the better solution. Right, so what's next? So swapping out some of our table production for chairs reduces waste without affecting the revenue. This version, this system, is called the ordered criterion method or the lexicographic method. It just means that we have some list of objective functions that we care about, and every time there's a tie in our first, and it's an ordered list, we care about one more than we care about two, more than we care about three, etc. Every time there's a tie in our first objective, then we consider our second objective. If there's still a tie, consider the third objective, and on until we break that tie somewhere along the line. It's a popular method for breaking ties, like we've done here, but it's not particularly powerful, per se. It doesn't give us as many options as the next method we'll talk about. So after a few months of using this new solution that our new manager found, she manages to convince the owners of the wood shop that reducing waste is worth a small loss in profit. And the owners concede to a 30% loss. And our manager gets to work on a new model, a new LP to do this with, or to find the best solution within this new feasible region. So she already knows that the optimal profit is $96,000. Because what we found up here, we found 48 here, but we divided the objective function by 2,000. So 48 times 2,000 is 96,000. Yeah. So the profit function of the optimal solution, we plug it into here, and we have just the original profit objective function on the right side, or the left-hand side. And then we want our profit to be at least 30% of the optimal solution. So we use A equals 0.7. which is a 30% loss in profit. Because 0.7 plus 0.3 is 100%. So, yeah. And then we just have the same original polyhedron we had for the first initial problem down below, and our waste function in the objective. So this new constraint limits our solution to anything that had at least 70% of the maximum possible revenue. So this is our new feasible region here in the darker shade. And you can see that it restricts our feasible region. And again, I've drawn the contours of the waste function. Here it's a minimization problem, so the gradient is this direction, but we want to go against the gradient. We can see that this solution here is optimal. I'm going to solve it graphically here, but obviously we can solve it mathematically with the simplex. This is the solution. This is x equals 5, y equals 10, f is 68,000, w equals 78. So we've reduced waste at the cost of revenue. So this idea is called the benchmark or the rollover method. Because what we do is we choose a benchmark for our sort of primary objective function, in this case profit or revenue, and then we roll that benchmark down into the constraints, and then we optimize for the second objective, in this case waste. Notice that if we set alpha to 1, the rollover method is actually equivalent to the lexicographic method. So let me demonstrate that. If alpha equaled 1, then the profit would have to be at least as big as the optimal profit. It can't be any bigger than the optimal profit, so it has to be exactly equal to optimal profit, which is going to be the same idea as the lexicographic method. So the rollover is sort of a generalization of the lexicographic method. Either approach here requires that we know an optimal value for the first objective function. So the problem needs to be solved at least twice. Or at least once for every objective function that we roll into the constraints. This is not a big deal for a small problem like what we've just done, but if you have a large problem that takes days to solve, suddenly it might be a bigger issue. So what I think is interesting is that our rollover solution is not an extreme point to the original feasible region. So if we look at that again, the original feasible region is the bigger region here. That red point is not an extreme point to it. It's extreme to its own smaller feasible region, its own rollover region, but not to the original region. So when we're dealing with multiple objectives, in this sort of way, we may not get an extreme point to our original problem. And that's interesting. It raises some questions about what exactly is an optimal solution geometrically now. How do we know which, if we have these two objectives that we care about, how do we know which point is optimal? So we're going to have a definition here. This is a little bit technical. Given a set P and some number of functions f that map P onto the real numbers that we want to maximize, we call a point x that's in P, we call it Pareto optimal or Pareto efficient if there does not exist another point in P such that this second point is strictly bigger than f, this new point is strictly better than our original point for some I, for some objective, and our new point is no worse than our original point for all other objective functions. That is, x is Pareto efficient if we cannot improve one objective without making some other objective worse. Let me say that again. We cannot make any objective better without making some objective worse. If that's true for a point, then that point is Pareto efficient or Pareto optimal, depending on who you ask. So let's explore that. We call it the Pareto frontier is the set of all Pareto optimal points for a given problem. So let's explore that, the definition. We have a few points here that I've marked out on our feasible region. And we have both of our objective functions laid out as level sets in the background. They're probably pretty hard to see. We're going to systematically look at all of these points. So let's start with the one in the middle. That guy. Well, what's the problem? We can see that if we were to push it this way along the level set for either objective, we would improve that objective, or we would improve the other objective because they're not quite parallel, without affecting the other objective. So let me be a little more explicit here. So this is sort of the direction of, if we move in that direction, we are parallel to the profit level set. So if we move in that direction, we are not changing the profit at all. If we move in this new yellow direction, which is slightly off from parallel, we don't change the waste at all. So if we're looking at this point in the middle, we can move in the waste direction. And we pull away slightly from the profit direction. So let me demonstrate that. You can see that they're not quite parallel. The yellow waste direction, if we're parallel to the waste direction, then we're actually very slightly increasing profit. So in other words, I'm going to mark this as 1. So at 1, we can improve profit without altering waste, without increasing waste. So let's go back to our definition of Pareto efficient. If f is our profit, or if I is our profit function, we have that this new point, whatever new point on that waste vector, has a better profit and the same waste. And a point is Pareto efficient if there does not exist such a point like that. In this example, there does exist such a point, any point on this yellow vector. So, no, it's not Pareto efficient. And we're going to sort of compare each of these, points in the same sort of way. Down here below, we have the same deal. No. We can do exactly the same thing for that point as we did for the point above. What about this point? Well, in this case, we can't follow the waste vector, but we can follow the profit vector. If following the profit vector, we're actually slightly decreasing the waste. So we can improve waste without losing profit. And the same is of course true for this point here on the edge. So these are both no's. Maybe I should have done that in a different color, but whatever. What about this point here at this vertex, or at that extreme point? Well, here, following either the red, or the green, or the yellow vector becomes infeasible immediately. What does that mean? Well, remember from the rollover method that we found an objective or a solution here-ish that had a better waste but a worse profit. Obviously, any point in the sort of interior is bad, so it is not Pareto efficient. So if we were to sort of move in any of these directions, that's not going to find us a Pareto efficient point. But if we were to move in this direction along the constraint, what happens? We increase, or we improve waste, but we decrease profit. So in any direction we move from that point, we might decrease waste, but we are also going to decrease profit. So 3, decrease waste. Well, I don't need to do that. This point is actually Pareto efficient. And by similar logic, we can see that this point is also Pareto efficient. So 3, decreasing waste. Requires decreasing profit. And for the second point, we have or in fact, and vice versa. So increasing profit requires decreasing waste, or increasing waste as well. So these points are Pareto efficient. What about that point? Well, we have a similar sort of argument. We can't continue in the same direction, but if we move down, straight down this constraint, we're still decreasing waste. We're also still decreasing profit. But that's the only sort of direction we can move that we haven't already explored. If we move this direction, we're increasing profit, but we're also increasing waste. So, yes, Pareto efficient. And in fact, this point is also Pareto efficient. Again, going down decreases waste, but we're not producing as many things, so we're decreasing profit. What about the origin? Well, the origin has minimal waste. Its waste is 0. So if we move off of it to increase profit, we're increasing waste, no matter what direction we move. So actually, yes, it is Pareto efficient. So that's neat, that the origin is Pareto efficient. So what I did is I did the rollover method, I think maybe 100 or so times, with different values of alpha. And enumerated the entire Pareto frontier for this problem, or I got many of the points that are on the Pareto frontier. So by varying alpha in the rollover method, it's possible to generate many efficient solutions. Unfortunately, not all of these solutions are efficient. So these solutions over here are not actually Pareto efficient. And these happened when alpha was very close to, was it 1 or 0? I think it must have been 1, though I'm not positive. So when alpha was approaching 1, we got a sort of inefficient point. And that's due to machine precision error more than anything. The rollover method generalizes to an entire field of optimization called goal programming. We might talk a little bit about it in DOR2. I'm not sure yet. But it's a neat field with a lot of neat applications, especially to the business world. Goal programming is very popular there. Yeah. It's more common to see the Pareto frontier plotted against its objectives. So here I took all of the same solutions, found both of their objective function values, because remember there are 2 objective functions here, profit and waste, and plotted those against each other. And we can see this little tail here corresponds to a little nub there. Now let's think about this a little bit. Waste is being minimized, or we want to minimize waste. Minimize, but we want to maximize revenue. So if we had a point here on the Pareto frontier, or correction, let's plot a point here. Suppose we had a solution that gave us that objective function value. Well, it has the same revenue as this point. But it wastes a lot more. So, same profit, but more waste. So this is not Pareto efficient. We can also see that it has the same waste as this point, but less profit. So by both of those standards, it's not Pareto efficient. And ultimately, we can use that same logic to prove that anything on this sort of side of our frontier is not Pareto efficient. And there are plenty of solutions that could fit in there, plenty of feasible solutions that could fit in there. But we'd never found a solution that fits on this side of the frontier. So this is infeasible. There we go. We do also see right here there is sort of a crook or an elbow. That corresponds to, I believe, this point here. Elbows are sometimes very important for business applications. They indicate sort of a change in rate of waste to revenue. A lot of methods that are looking for the best solution will look for the most aggressive or the least aggressive elbow in the Pareto frontier. That's a popular method for finding the best solution. So there's one more method we haven't talked about yet, and that's scalarization. So one of the owners of our workshop, he decides to explore possible planing methods by himself. So he implements the multi-objective method that he remembers from linear programming called scalarization, and he picks some constant lambda in 0 to 1 and takes a convex combination, or you don't necessarily need a convex combination. It could be just a linear combination. The difference is that a linear combination is not bounded by 0 to 1. It can take any number. Lambda could be any number. So he wants to combine the two objectives by taking a convex combination of our two objectives, profit and waste. And actually, I think this should be maximize the negative of the waste. Because remember, profit we're trying to maximize, waste we're trying to minimize. So the negative of a minimize is a maximize. So we can combine them thusly. This is another very popular method. Excuse me. Because it's simple. We only need to solve the problem once. Remember, for the rollover method, we had to solve the problem for our first objective so that we could find an upper bound to benchmark based off of. Same for the lexicographic method. And every objective that we want to roll over needs to be solved for as its own problem. If we scalarize it like this, we don't have to do that. So this is really beneficial if we already know how much we care about one objective over another. It falls short in that it doesn't necessarily produce the Pareto frontier in the same way that the lexicographic method does. Uh, and there's no way of sort of limiting how far one objective can fall. You could combine the two and use a rollover with scalarization, but scalarization by itself doesn't limit. That's not a T, that's an L. Doesn't limit not improvement, but decrease in objectives, like the rollover does. Still popular, and in fact, we'll show you where I've used it in the past. Yeah, so here is, the next slide gives us this. So we had lambda times the profit minus 1 minus lambda times the waste. If lambda equals 1, we're just going to be left with, so if lambda equals 1, we're just left with f. We're just maximizing profit again. Which means that any of these solutions are optimal to lambda equals 1. If we have, now let's say we have lambda equals 0, we just want to minimize waste, we're going to be left with this point, the origin, because it has 0 waste. What if we have something in between? Well, this method is performed or this method does not alter the feasible region. And so it only returns extreme points. Of the original problem. So it will return this point and this point somewhere. I don't know exactly where the flip is, but for some lambda in 0, actually, yeah, this point is returned for, or is optimal for lambda in 0 to some number. I'm going to call it beta. This point is optimal for some lambda in beta to gamma. And this point is optimal for some lambda in, actually it should be inclusive, I think, gamma to 1. So it's only ever going to return extreme points because the simplex method only ever returns extreme points, and we didn't change the feasible region. So the only points on the frontier that we're going to find are these 3 points. And maybe that's all you care about. But maybe not. Maybe you want to see some more. Okay, so we've seen all of these methods. They're nice, but the problem that we explored them in is not difficult, and it's not really practically sized. There are so many more things to worry about in a real planning sort of problem. So I have a few examples of when the Pareto frontier is actually useful. It's actually important. First one is actually from my own research that I've been doing with a political districting group here on campus. Here what we've done is we have a heuristic. So political districting is mathematically a very, very big problem, and it doesn't take well to linear programming because it has to be an integer program, which automatically takes a lot of time. It's a very large integer program, and it doesn't have a linear objective function in our case, the way we did it. The objective we care about in this research is not linear. So instead of using simplex, we used a hill climbing algorithm, or hill climbing heuristic, really, which looks for maximums just by comparing solutions. And it actually works pretty well. The problem is it doesn't necessarily find the optimal solution. It's very good at finding improvements on solutions, but it does not necessarily find the optimal solution. So we actually used scalarization. We had two objectives we cared about. The compactness of each district, here on the x-axis for each of these plots, and the expected number of black representatives in total for the state on the y-axis. And we ran this, we scalarized this. We said the red dots are 100%, we only care about the compactness of a district. The green dots are, we only care about the expected number of black representatives. Let's maximize that. And everything in between is a convex combination of those two objectives. So we're sort of looking for the Pareto frontier here. And I said that it only finds extreme points to problems. Scalarization only finds extreme points. So I may not get the entire Pareto frontier, but this is a heuristic, not an algorithm. It does not necessarily find the optimal solution, so we may not even find, so we don't really care. It's not necessarily going to find extreme points because it's not simplex. And two, there are so many possible solutions, so many extreme points, that we don't necessarily care about the things in between. So scalarization works really well here, and gives us sort of a view of trade-off, how hard it would be to create a convincing, compact-looking racial gerrymander. So here we see that we can, in Mississippi, we can have a high expected number of black representatives that doesn't lose very much compactness. Whereas in somewhere like Georgia, compactness is just a measure of how circular the district looks. So if the district looks like a circle, it's a 1. If it looks like a squiggle, like a classic gerrymander, it has a low compactness score. So, but in Georgia, if we want a large number of black representatives, we have to lose some compactness. So that's some sort of interesting results that we found using multi-objective optimization, using scalarization, looking at the Pareto frontier. I have a few more examples that I'm not personally invested in. I mentioned that the Pareto frontier is used a lot in the business world. This comes from a portfolio optimization problem. And here the maximum Sharpe ratio is sort of looking for those elbows I mentioned before. So yeah, this is a plot of expected return versus probability of collapse of the portfolio. Very common application. If you're designing an aircraft or any vehicle really, there are things maybe you care about more than others. If it's a spy plane, um, you care about how far it can go um, in a certain speed range, in this case in the transonic range. If you're making a fighter aircraft, maybe you care more about how quickly and how long it can endure a turn for. So maybe you create a few designs, test them, and plot their, or simulate them somehow, and plot their sort of range versus turn rate um, abilities. And for some reason, my citations disappeared. That's unfortunate. I'll try to, I'll fix that. I'll upload the citations in case any of you care to look at these. They're interesting papers. Vehicle dynamics. Again, if you're designing a race car, um, maybe you care about how quickly it can make a 100-meter turn, or a 100-foot radius turn, or a 400-foot radius turn to prepare for different sorts of courses. Maybe you have a different suspension setup, different tire setup. You might like to look at the Pareto frontier and see sort of which ones are unilaterally better than others, which setups. And of course you can do this for many, many more objectives. All of these examples are unfortunately in 2 dimensions, but you could have 3 objectives. Maybe you care about the lap time on a 100-meter radius, or 100-foot radius, a 400-foot radius. Maybe you also care about time between refuels of a given setup. That could be a 3rd dimension to this problem um, that a race car driver might care about. Um, this is a neat one. This comes from different ways of a paper exploring different ways of manufacturing concrete, comparing its cost to its CO2 emission um, in the creation process, and sort of extrapolating or interpolating its Pareto frontier. And my references are gone, but those are all the examples I have. I'll stick around for any questions, but that's all the content I have for today, so you guys are free to go.